In this video, we take a deeper dive into the first technique for solving string-related questions, linear time string matching. So there are three linear time string matching algorithms, KMP, Boyer-Moore, and Rabin-Karp. Out of those three, Rabin-Karp is the simplest and easiest to understand, so that's why we're going to focus on knowing this one. So what we're going to go over in this video is really, what is linear time string matching? Why do I need to know this? And how can I gain an intuitive understanding whenever this comes up in an interview to actually be able to solve the question? So let's start with an example. Let's say that we have a block of text T and that it has a decently sized length. And then we have a search string S, and that is of a smaller length. Let's say that S has 3 characters in it, just E, 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 and T has a lot of characters in it. Let's do E, E, S, E, E, R, E, E, and then finally about the E. So this question has a lot of different flavors. Find the first occurrence of S in T, or find how many times S fits in, or how many times you have an S in T. Those are just 2 flavors. At the end of the day, you're matching, right? You have a string and you want to match it in this other block of text or other string in linear time. So first, let's talk about nonlinear time. What is the very naive algorithm? The very naive algorithm is to iterate through T, and as you're iterating through T, see if you match the first character of S, and if you do, just keep moving along. So we start here, we match, we go on to the next one, we go on to the next one, okay. We realize it's not the same because EE is not the same as EES. So now we go to the second position. We were here, we go to the second position, now we check ESE and EEE, the first one match, then we're going to go into S again. As you can see, we're repeating. We're going through S many times, we're going backwards in T, and this algorithm ends up being nonlinear. It is big O, T, S. Non-ideal. So you're in an interview and you want to come up with an ideal algorithm, you want to intuitively get that really quickly. The neat part about the Rabin-Karp algorithm is that it is really easy to understand. And the key insight is incremental hashing. We'll get into that, what that looks like more in a second, but first, at a very high level, what we're going to do is every single character inside of S, we're going to put it through a hash function, and we're going to add every single character. So put all these through hashes, and then add all the characters, and we're going to get a value, let's say 52. So then here, every single string of size 3, we put through a similar hashing function, and we see if they match up. So E, E, S, let's say we put all those through the same hashing function, we add them up, and we're going to get a value equals to, let's say 58. So we know that 52, 58, there's no way these are the same string. So what we can do now is just say, we don't have to go over S and go backwards in T. We simply go forwards in T again, and now we have ESE, and we calculate the hash of that and compare that to EEE. And once we have a match in the hash, 52 equals 52, we'll get that here. Then we can compare character by character. And you still have to compare character by character because you could have a hash collision. So at a very high level, let's step back. Instead of the naive approach, which is going character by character, and going backwards in T, iterating through S many times, we hash S once, and we go through T once, and at each single character, all we're doing is calculating the hash and comparing the hash. And then once you get a match, then you do the comparison. That leads to a big O of T plus S, but I'm assuming that S is smaller than T, so a big O in terms of T algorithm. Much better, linear time, string matching, Rabin-Karp. Cool. So I want to go one level deeper into the most challenging part of actually implementing this algorithm, and that is with the incremental hash. Incremental hash. So why is this challenging? It's challenging because So we've gotten to this point where we have 58. Now what we have to do is we have to basically remove the contribution that this character had in my hash and add the contribution that this character has in my hash, such that now these three characters should match with these. If they match with these three characters, I should get the same hash value. But that becomes challenging when your hashing includes an index. So here, and we'll get into, and the reason that you use index, let's first start there, right, is because if you have a very naive hashing algorithm, which we're going to implement really quickly, you're going to get a lot of collisions, and you're not going to get the benefits of a truly linear time string matching algorithm. So let's start with a super naive incremental hashing technique, and then we'll get into one that's maybe more practical. Not super advanced, but more practical, right? So the most naive approach is saying, okay, what if we just calculate the ASCII character value of each of these characters, right? So if I have E, and I just add those up, let's say, I don't know, for sake of simplicity, let's say 2, 2, 2, and I get it equal to, and I get it equal to 246, right? So now when I go over here and I have S, 2, 2, and 15, or whatever S represents, right? It's not going to be equal to 6. So now what I can do is I can subtract 2, and then now I have 2 plus, let's say I have 2, 2, and this was 8. I don't know exactly what I said. I subtract 2, and then we add these three elements, 2, 8, and 2 again, and that doesn't equal to our 6, so we subtract this, we go here, let's say R is 7, eventually we're going to get to 2, 2, 2, and we'll have subtracted all of these elements out, and we hit 2, 2, 2 equals 6, and that equals 6. So that's a super naive way to incremental hashing algorithm, but you can see it's linear time. All we're doing is we're subtracting a number and adding a number at each iteration. But the problem with this is, what if I have FEE and EFE, right? The character values of all three, if I just add them up, are the exact same. So we use index in this hashing algorithm in order to basically guarantee the positions are the same whenever we're making this calculation. So that's where it gets a little bit harder, and I wanted to talk about a little bit of math, a common formula that people use for incremental hashing, and I'm going to write out basically the key components that you would need to actually code this up, right? So incremental hashing, we have, let's say we're calculating T hash, and this is one that's going to be continuously moving. We're going to say T hash is going to, I'm going to say plus equals, I know you might not see the plus equals, and we are going to add the current T hash that we had before plus, or let's actually do it times some constant. Let's call that constant base. So T hash times base plus whatever the current T hash, whatever the current character is at. Sorry for the smudge here. I do not know if I can fix that. Let's shuffle it a little more. Okay, plus whatever the T is, dot char at, and we want to do char at, let's say the current position that we're at is just I. So, okay, so what we've done so far is we've written a formula, right? And what this is going to do is, let's say T hash starts at 0, so we're going to start it at 0. I don't know exactly where to write that, but I don't know, let's say it starts at 0. And every single index that we're going to go through, what we're going to do is we're going to add, so 0 times some base, and then we're going to add t.char at I. So that's E is going to give us 2. So our first iteration is going to be 2. Then we're going to plus equals 2 times some base plus t.char at the next position. And then all of that's going to be multiplied by base plus t.char at the next position. All right, so I'm going to write out the important part of this, I guess, formula, what I'm really getting to. Because the challenge is really, okay, so we're also going to calculate S hash with the exact same formula, right? So our base, our value for S hash, is going to be relatively small because we're starting at 0 and we're going to multiply times the base. We're going to add s dot char at this, so 2 times some base plus the char at this plus 2, that times base. But then later on here, we're going to have, we're going to be multiplying t hash times a base, and we're going to continue multiplying that by that base. So this is going to have like a large contribution to the overall number value. So the real question is, how do we get rid of these lower values and add the next value? And I'm going to kind of explain that, and I will write out kind of the formula of what this looks like and how to make it a little bit more easy to understand. So we're going to have, let's say t hash and t hash times our base value plus t dot char at I, and eventually all of this is now going to be the next t hash. So this is going to be times the base plus t dot char at I, and then eventually all of this is going to be the t hash, and then we're going to multiply it by the base, and then plus dot 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 dot, right? So what you're going to notice now is I'm going over how are we going to remove this element when we're continuously using the index to as part of this calculation that's going to calculate t hash. And now I'm with the index way down here. How are we going to remove this value from the overall calculation? So what you can see here is if we do a little bit of multiplication, which I promise you is not that hard. In the beginning, our t hash is going to start at 0. Right? So let's just remove this times this, and we just have t dot char at I. So we're going to have t dot char at I times base. So we're going to have base times t dot char at I and base times t dot I plus t dot char at I times base, right? So really, I'll actually write that out, times plus t dot char at I, base, this went to 0, so we went base times t dot char at I, plus t dot char at I, and now we're multiplying that by base again, plus t dot char at I. So we're going to have times base here, and this other base is also going to be now squared, and now we're going to have plus this thing that I had here, the t dot char at I. Okay, so now let's take a second. The first position that we had, which is this initial I should have wrote I plus 1 and then I plus 2. So the first position that we had, in order to get rid of the value, we basically need to subtract this part from the equation. If we subtract this, then we only have the contribution from this element, this, and this element. So now what we can do is we can keep track, and this is like the key here, is really to keep track of something like some variable and what that variable is basically base to the s minus 1. And this is basically what you are going to want to subtract to. Our length is 3, 1, 2, 3, and we're going to basically subtract base squared and this element. So when we subtract base squared and this element, at every single iteration, if we're trying to extend our window, basically what we're going to be doing is we're going to subtract base raised to the s minus 1 plus, times the value at the index, so let's just say the I, that you are trying to remove. So when you subtract this, you get rid of this, and now you put this through this function again, and what that gives you is t.char I plus 1, all of this, times, base plus the next char. Now this is going to have the times the base square that this had before, plus this times base, plus this char right here. But we're going to get back to this equation right here. But, I hope that I conveyed that at every single iteration, I'm showing you the math underneath the code that needs to be written in order to, and what needs to be kept track of in order to basically move nicely from, with this window, next to this window, next to this window, and to be able to subtract the value here, and the base raised to the s minus 1, which doesn't give us base squared, times the t.char I value at the index that you're trying to subtract from. That's going to take this away, you're going to get this, and now you can put this back through this function, and you'll get this again, right? So that's just kind of some fun math that kind of, I believe, explains pretty intuitively of how to implement an incremental hash function that is not super naive. So stepping back again, we have linear time string matching, and we first understood what that was, why it's needed, what it looks like, different flavors, and then we went into the hardest part of implementing that algorithm, and that is really understanding how to write an incremental hash function and the math underneath what you have to keep track of and what you have to have in your head. And the last thing that I want to leave you all with is a statement that I really stand by, and what that statement is learning begins where teaching ends. And I want you all to really think about that. Me going through this, it's not going to stick. It's not going to be super intuitive to you. You have to use this and you have to implement it yourself. And that is why I'm not writing up the code. That would take, in my opinion, that would really steal the opportunity of really gaining that understanding and gaining that learning at the very fundamental level. So instead of that, what I've done is provided the environment, the play, the area where you can experiment, where you click a single button on this YouTube link, and it's a GitHub project. You click a single button and you will do a question that requires an understanding of the Robin-Karp algorithm. So I'll set up provided below, and I really recommend if you want to understand this and you want to implement it and you want to make it more crisp in your mind, what you really need to do is you need to play with it. You need to implement it, you need to experiment with it, and only then does it become intuitive. So everything that I do is about finding the most effective way to help you all learn and become a master of the technical coding interview in the most effective way. And you can either grind leak code questions, or you can clearly identify these concepts, this understanding, the things that continuously pop up in the interview. And I clearly identify those and then do questions and really play with using those concepts to solve real technical coding interview questions. And that's what this is all about. So if you have any questions, reach out, YouTube, Twitter, email, I have office hours, all of that. I'm more than willing to help and more than excited to help. Have a great rest of your day, and thank you.